All right, so in the last video, towards the end, we introduced the idea of a solution vector for a system of equations. And what I want to do is an example where we're verifying that a given vector is a solution vector. Okay, so here we have a given vector, a given solution vector, x is equal to 1, 3 times e of t plus 4, negative 4 t e of t, and we're asked to show that this is a solution to this system of equations. Now, at first glance, especially if you're not terribly familiar working with matrices, you might look at this and think, well, that doesn't look like a column vector. You know, it looks like a couple of column vectors with some multiplication happening. Like, that doesn't look like what I'm expecting it to look like. But if you perform these operations, so I'm going to do this up here. The functions e of t and te of t, these are like scalars that get multiplied into the entries of that matrix. And so what this really looks like is the matrix e to the t, 3e to the t, plus 4t e to the t, negative 4t e to the t, and then adding matrices together is done component-wise or entry-wise. So this is the same thing as e to the t plus 4t e to the t, and 3e to the t minus 4t e to the t. That should look like an exponent. Okay? So this thing that's appearing on the right-hand side here is the same thing as this, and this is a column vector. It is a column matrix because it's a 2 by 1 matrix. Even though the entries look complicated, there's only one entry appearing in each row. So this is just kind of the preferred notation for something like this. And again, we're asked to show that that this is a solution to this system. We verify that it's a solution the same way that we verify that a given function is a solution for just a single differential equation, by plugging it in. So what does that look like for us? Well, I have x, right? And x is given to me here, but I've also represented x as a single column matrix instead of this form that it's appearing in right here. And when it's in this form, let me rewrite that here. X is equal to e to the t plus 4t e to the t, 3e to the t minus 4t e to the t. I can evaluate x prime with this matrix in this form. So x prime, what would that look like? Remember, I'm just differentiating each one of these with respect to t. So this is going to look like e to the t plus 4e to the t plus 4t e to the t. And I'll simplify that in a second. This guy's going to look like 3e to the t, make that a little bit more clear, minus 4e to the t, minus 4t e to the t, and doing a little bit of simplification here, this is going to look like 5e to the t plus 4t e to the t. This is going to look like negative e to the t minus 4t e to the t. Okay? So again, I'm putting these things in this form of a kind of a single matrix instead of a couple of matrices that we're doing operations on, to more easily substitute them into this guy. Okay, so let me substitute this into the left-hand side. And actually, let's work with the right-hand side first, because that's the side that there's actual work to do. I have to multiply the matrix 2, 1, negative 1, 0 by the matrix x, which we have explicitly right here. E to the t plus 4t e to the t, 3e to the t minus 4t e to the t. Okay, this is a column matrix, and again, the way that we multiply these two matrices together is we imagine picking this matrix up, turning it, and dropping it on these entries. So this 2 is going to get multiplied to that entry. This is equal to 2 times e to the t plus 4t e to the t plus 1, this entry, times this second entry down here, 3e to the t minus 4t e to the t. And then I'm going to do the same thing. I'm going to pick up this column matrix and drop it on the second row here. That's going to look like -1 times that. So -1 times e to the t plus 4t e to the t plus 0 times this second entry, and that's just 0, so I'm not going to write that. Let's simplify this now. So I have a 2e to the t plus a 3e to the t after distributing. So these are going to combine to give me a 5e to the t. And then I'm going to have an 8t e to the t minus 4t e to the t after distributing. That's equal to plus 4t e to the t. And then here, just distributing the minus 1 in is going to give me negative e to the t minus 4t e to the t. And notice that this matches x prime, which shows that the right-hand side of this equation equals the left-hand side of that equation once I do that substitution. Okay? So that worked out pretty nicely. Now, one thing I want to point out, which we'll do this in future examples, is that I didn't actually need to put x into this form to find x prime. I actually could have differentiated from here, from it looking like this. And I'm not going to go into a deep explanation as to why, because you can probably figure this out for yourself. But if you treat these matrices, the 1, 3 here and the 4, -4 here, as just constants, you can differentiate this thing as you would a normal function of a single variable. The derivative of this term is literally just 1, 3 e to the t. And the derivative of this term is just the matrix 4, -4 times the derivative of this function, which would require the product rule. You can do that and then show by combining everything that you still get this matrix. So basically all that is to say is that you can differentiate this thing as is. You don't have to put it in this form that I was using in this example. Okay? Let's go ahead and move on. So, okay, so let's suppose that we have some number t naught in an interval I, and the vector that we've defined before, that x, which holds all of our unknown functions that we're trying to solve for, we think of that as a function of t, because if I'm plugging in a particular value of t into this, that implies that I'm plugging that particular value of t into each of my entry functions here. So x of t naught would correspond to this, x1 of t naught, x2 of t naught, and so on and so forth. And if we define x naught, so notice this is different from x of t naught, the notation is, to be equal to this matrix of constants, gamma 1, gamma 2, blah, 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 just some matrix, some column matrix consisting of n constants. If I were to set this guy equal to this guy, then that's the same thing as creating an initial condition for each of those equations in my system. So we can turn these systems of linear DEs into initial value problems, into IVPs, by introducing something like this. So the problem x prime equals ax plus f, which is, remember, that's the general way of denoting a linear system of equations, subject to this condition x of t naught equals x naught. You know, and think about what this is saying. This is setting up initial conditions for each equation. x1 of t naught equals some constant. x2 of t naught equals some constant, and so on and so forth. That's what we're going to be calling an initial value problem, just like the terminology we've been using. Okay? Now from here forward, we're going to be talking about just a whole bunch of definitions and theorems. And we're going to be kind of blasting through them pretty quickly. And the reason for that is what I said at the beginning of the first video for this section. It's that, for the most part, these theorems and definitions and whatnot are the analogs of what we've already talked about in 4.1, but adapted to the case of a system of equations. Okay? So everything that we're covering right now should feel pretty familiar. We're just now talking about it in the context of systems. Let's start with this first theorem, the existence of a unique solution. So if we're going to let the entries of our matrices A of t and F of t in this equation up here be functions that are continuous on some common interval that contains the point t naught. Okay, then there exists a unique solution of the initial value problem, and it says 7 on the interval. So obviously this was copied out of your book. That 7 is referencing this right here. All right. We had an existence theorem like this in 4.1 as well, with similar conditions. But again, what this is saying is that if this coefficient matrix and this matrix consisting of those functions of t are both continuous on some interval containing this input that we're using for our initial conditions, then we have a guarantee that this initial value problem has not just a solution, but a unique one. It has a single solution. Okay, so that existence theorem is important because that's what motivates us to look further. If we know that there's going to be a solution, a unique solution to an initial value problem like this, then that says we should now try to figure out how to find that solution. Okay. Now, like I said, a whole lot more theorems and definitions to talk about, and implicit in the definitions and theorems that follow is this. So we're going to assume from here forward that whenever you see the notation here for a coefficient aij and one of those functions fi, we're going to assume that they are continuous functions on a common interval I. That's what's going to allow us to use the theorem we just talked about in these results. And you're going to notice we're not really proving a lot of this stuff, and that's simply because of one of two reasons. One, the theorem might have a proof that's beyond the scope of this course, similar to what we saw in section 4.1. So the existence of a unique solution, for example, proving that might require some techniques that are beyond what we cover in this class, but we still need the results, so we're talking about it. Or the proof might be so similar to what we already saw in section 4.1 that there's no point in going over it again. So, like I said, we're going to kind of move through this somewhat quickly. This next theorem is the superposition principle, which is the analog of the same principle we saw in 4.1. Let's suppose that we have a set of solutions, x1 through xk, and it says the homogeneous system 5 on an interval I. The homogeneous system here is just any homogeneous system of linear equations. It does not have to be k equations. It's just any number of equations. But suppose we have a handful of solutions to that homogeneous system, okay, k in particular. Then just like what we saw in 4.1, any linear combination of those solutions, which again is anything that looks like this, x equals some constant c1 times the matrix x1 plus c2 x2 plus so on and so forth until we get to ck xk, is guaranteed to also be a solution to that system. Okay, so that's the superposition principle. And what that means is that if we've found, you know, one or even two solutions to a system of equations, we can turn that single solution or that pair of solutions or however many you found into an infinite number by forming all of the linear combinations that exist of those. Next up, we have linear dependence and linear independence, which is defined much in the same way that we did in section 4.1. So again, if we have a set of solution vectors x1 through xk of some homogeneous linear system on a common interval I, then we would say that this set of solutions, remember these are column matrices. They're not just functions of t. They're column matrices where all of the entries are functions of t. We say that this set of matrices is linearly dependent on that interval I if there exist constant c1 through ck, not all of which are 0, such that that linear combination that we're seeing here equals the 0 matrix. Now, this is the same way that we defined linear dependence back in 4.1. The only difference there was that instead of dealing with matrices whose entries are functions, we are now dealing with my My phone is having an issue with its charger right now, so I'm getting a little distracted. We were here where we're dealing with matrices. Back then we were just dealing with single functions. Okay, but the definition is essentially the same thing. If no such group of constants exists, so in other words, if all of these scalars have to equal 0 in order for this to be true, then we call that set of solutions linearly independent. Okay? I'm going to actually cut this video a little bit short. My recording device, aka my phone, is about to die, so I need to fix that, and then we'll pick this back up again.